Welcome back to another MECH 1000 video. We are in Unit 9 in the Blueprint Reading textbook, where we are learning about threaded hole specifications. And so we're going to resume this video by looking at another exercise from the textbook. And we're going to start with the first question here. What type of section view was used? So we're hitting on some questions from previous chapters just as a review. We've talked about the different types of sections. And in this particular instance, we can see the section is right here. It's right on top of the drawing itself. It's as if we sliced through the view here and then took that section view and revolved it 90 degrees so that now we can see what the cross-section of this member looks like. And so that is called a revolved section view. We also, I think it's also a good idea to remind ourselves that not all of the information that we need to find is in the drawing itself. A lot of times that information can be found in the title block. And the material that the object is made of is frequently in the title block. And so the question is asking what type of aluminum was specified. We can see here it's 3003-H12. So again, this is not a materials class. We're not going to spend a lot of time talking about different types of cast iron or different types of aluminum, but we do need to be able to read the drawing. And all I'll say is that aluminum, although it is an element from the periodic table, is very rarely used in its pure form. It's usually an alloy of some type mixed with other metals, and so there are probably hundreds of different types of aluminum. And so that 3003-H12 is just indicating the specific aluminum alloy that was being used. Okay, let's get back to threaded holes as we were discussing earlier. How many threaded holes does this object contain? So when we see a hole with a dashed line around it, that is used to indicate the presence of threads. But as I mentioned before, we need to make sure that that's truly what we're seeing, because if the hole had a chamfer or a countersink or counterbore or some other type of feature like that, and it was on the back side of the part, it would show up as a hidden line and would look very similar. So when we see those that dashed line surrounding the circle, what we need to do is we need to take a look at the note to make sure that we actually see a thread type being specified. I'm looking for that UNC, and I found it. So yes, this is a threaded hole, and the note tells us that that is true for these 4 holes. So we've got 1, 2, 3, and 4. Now, it looks like there are a couple little holes here that also have dashed lines surrounding them. If I look at their hole note, we can see, yes, again, we've got UNC holes, and that's true for these 2 holes. So that brings us up to 5 and 6. And now let's look at the front view. We do see a dashed line surrounding these 2 holes. If we come down here to the hole note, no threads is specified. What it does have is a counterbore on the far side. So that dashed line that we're seeing right there is not representing threads. That's representing a counterbore that's on the back side of this view. And I don't see any other holes here that have any threads designated. So it looks like 1, 2, 3, 4, 5, 6, and that is the correct answer. Okay. I know it's difficult to tell just by looking at this chart because the chart doesn't have a header across the top of it. So this first column is the diameter, and then this is the decimal equivalent of that diameter. So that's the fraction form. And then this next column tells us the number of threads per inch, the tap drill, and what its decimal equivalent is. Okay, so when the question here asks what tap drill diameter is recommended for a 7/16-14 UNC threaded hole, 7/16 is the major diameter. And this, I should also say that all three of these pieces of information, these first three columns here, are all for UNC threads. So we've got our 7/16 inch diameter hole, 14 threads per inch for the UNC thread type. That's telling us we should use a U drill, the drill size that's designated by the letter U, which has a diameter of 0.368. What tap drill diameter is recommended for a 5/16-32 UNEF threaded hole? So over here, these three columns are for UNEF. These three are for UNF, and these three are for UNC. So if we look at our 5/16 inch diameter, and we come over here, that's UNC. Keep coming over here, that's UNF. Keep coming over here, and this is UNEF. That's our 32 threads per inch, which means we need a 9/32 drill bit to drill the tap hole. What is the major thread diameter of a number 4 unified thread? So again, the headers of these columns on this chart have been cut off, but this is the major diameter. And the second column is the decimal equivalent. So if we want to know for a number 4 thread, this is the number 4, that's the decimal equivalent, so its major diameter is 0.112. Which has the largest major diameter, a number 6 thread or a number 6 drill? This is a good question. This is something that students might easily confuse, the number 6 thread or a number 6 drill. So we've got the two different charts here. This chart to the right here, this is for the threads. This is the diameter. This is the decimal equivalent of it. This next column is the TPI, the tap drill, and then the decimal equivalent of that tap drill. And these are all UNC. So a number 6 thread would be right here, and it has a diameter of 0.138. So that's for the thread. This is from the chart for different size threads. This chart over here, again, the title up at the top has been cut off, but this is the chart for the drill sizes. These are all the drills. And so a number 6 drill is right there. And so we can see it has a diameter of 0.2040. So obviously 0.2040 is going to be bigger than 0.138. So it is the drill that is larger. All right, let's look at another practice exercise. What method of dimensioning was used for locating these holes? Now, our textbook calls these dimensions arrowless. But when you see these dimensions in AutoCAD, AutoCAD calls these ordinate. Ordinate. Sorry there. Okay, ordinate. So we had, there's a drawing in the AutoCAD textbook that is dimensioned, at least one. I think there are a couple that are dimensioned this way. So the way these ordinate dimensions work, or arrowless dimensions, as the blueprint reading book calls them, the bottom left corner of the drawing has the coordinates 0, 0. It's like the origin. And so what we do is we show along the horizontal x-axis all of these x coordinates, how far away from that lower left corner are these different features located. And then in the vertical direction, we have what their vertical actually, look, this one's different though, isn't it? It starts at 0 up here. So let me fix that. My mistake, I should have looked a little closer. So in this particular example, it's actually the top left corner that has the coordinates 0, 0. And so these are the x coordinates and these are the y coordinates. So for instance, if we wanted to locate this hole right here, the center of that hole has the coordinates 0.50, comma, negative 1.12. Okay, and that's relative to the top left corner. So it's a different system of dimensioning, but it does come up occasionally in, obviously, both the blueprint reading textbook and the AutoCAD textbook. What is the MMC of the 0.312 diameter holes? Okay, well, first of all, we have to find the 0.312 diameter holes. There's one. There's one. Okay, it looks like it's just these two. And they are both drilled. They both have this drilled abbreviation, which means when we refer to the title block to look for tolerances, even though they're both 3 decimal place dimensions, we instead need to look at the specific tolerances for drilled holes, and that's going to be plus 0.01 minus 0.002. So at MMC, we have more material. More material surrounding a hole makes the hole smaller. So 0.312 minus, our tolerance here says minus 0.002 in the small direction, leaves us with 0.310. So that's the MMC of that hole. How far apart are the counterbore hole and the countersunk hole from center to center? So here we see a countersink. Here we see a counterbore. And so if we want to know how far apart they are from center to center, so if I look in the horizontal direction, the distance between these two holes is just going to be 2.12 minus 1.38, and that gives me 0.74. If I look in the vertical direction, the distance between these two holes is 1.12 minus 0.62, and that's 0.5. So the center to center distance between these two holes, just makes a right triangle with sides of 0.74 and 0.65. So I can use the Pythagorean theorem, so square root of 0.74 squared plus 0.5 squared. Take the square root of that and it equals, I got 0.89 and the textbook has 0.88. I think that must be a typo. And I am out of time, so we are going to have to pick up this problem in the next video.